Hello everyone, I am Adarsha and along with my teammate Reshma GC, I am going to present our project titled EV ADAS Dashboard using STM32 Bluepill, PiximLab and Python Dashboard. Nowadays, electric vehicles are becoming more popular because they are environmentally friendly and reduce fuel consumption. However, EVs require continuous monitoring of important parameters such as battery level, temperature, speed, and vehicle safety. To solve this problem, we developed a real-time EV dashboard integrated with advanced driver assistance system features. This dashboard not only monitors vehicle performance but also provides safety alerts to assist the driver. During this presentation, I will explain the project overview, system architecture, EV and ADAS features, implementation, and finally the results and conclusion. Let's move to the second slide, which explains the project overview. In this slide, I will explain why we selected this project and what problem it solves. As we know, electric vehicles are becoming an important part of modern transportation. Since EVs depend completely on battery power, it is very important to continuously monitor their performance. If the driver cannot monitor the vehicle properly, problems like battery overheating, communication failure, or collision risk may occur. Our project solves this problem by providing a real-time monitoring dashboard. The dashboard continuously displays vehicle speed, battery state of charge, also called SOC, remaining driving range, motor temperature, fault status. Apart from EV monitoring, we have also integrated ADAS features. ADAS stands for Advanced Driver Assistance System. Its purpose is to move road safety by warning the driver before dangerous situation occur. Instead of checking different displays manually, the driver can see all important information on one dashboard. The main objectives of our project are to monitor EV parameters in real time, to improve driver safety using ADAS, to provide quick fault detection, to develop a low cost embedded solution using STM32. Overall, our project improves both vehicle performance and driving safety. Let's move to the system architecture where I will explain the complete system architecture. This slide explains the complete working flow of our project. Our system consists of four main components. First component is sensors. The sensors continuously measure different vehicle parameters such as speed, battery level, motor temperature and other operating conditions. These sensors collect real-time information from the vehicle. The second one is the STM32 Bluepill. The collected sensor data is sent to the STM32 Bluepill microcontroller. STM32 acts as the brain of our system. It receives all the inputs, processes the data, performs EV calculations, and also executes the ADAS algorithms. For example, it checks whether the vehicle is approaching another object too quickly or whether any fault has occurred. The third component is UART communication. After processing the data, STM32 sends the information through UART communication. UART stands for Universal Asynchronous Receiver Transmitter. The communication takes place every 100 milliseconds, ensuring the dashboard receives live updates without delay. The fourth component is the Python dashboard. Finally, the Python dashboard receives the data and displays it graphically. The driver can easily monitor all vehicle information in real time. This architecture provides accurate, reliable, and continuous monitoring of the electric vehicle. Let's move to the EV dynamics and ADAS features. This is one of the most important slides in our presentation because it explains the features of our project. In EV features, the dashboard continuously monitors vehicle speed, motor torque, battery state of charge, remaining driving range, different driving modes. This parameter helps the driver understand the current condition of the vehicle. Another important feature is regenerative braking. Normally, when we apply brakes, energy is wasted as heat. In regenerative braking, this energy is converted back into electrical energy and stored in the battery. This improves battery efficiency and increases the driving range. The ADAS features. Our dashboard also provides important driver assistance functions. The first feature is forward collision warning. If the vehicle comes too close to another vehicle, The system immediately warns the driver. The second feature is blind spot detection. Sometimes vehicles are present beside our car but are not visible through mirrors. Blind spot detection alerts the driver before changing lanes. The third feature is time to collision. This feature estimates how much time remains before a possible collision and helps the driver react quickly. The final feature is parking assistance. This helps the driver park the vehicle more safely. Apart from these features, our dashboard also detects battery overheating, communication errors, and other faults. Whenever a fault occurs, the dashboard immediately generates an alert. These features improves both safety and driving comfort. Let's move to the implementation. I will explain how we implemented this project. For embedded programming, we used STM32 Cube IDE. For hardware simulation, we used PiximLab. For developing the graphical dashboard, we used Python. The STM32 firmware uses different peripherals such as ADC, GPIO, UART, timers. The dashboard includes digital speedometer, battery indicator, live graphs, bird eyes view of the vehicle. We also included a UART shell which helps us test communication between STM32 and the dashboard. By combining embedded hardware with Python software, we achieved smooth real-time monitoring. The final slide for our presentation is results and conclusion. After implementing the project, we successfully achieved real-time monitoring of the electric vehicle. The dashboard updates approximately 10 times per second, providing smooth visualization. The system accurately displays vehicle parameters and successfully generates collision warnings, blind spot alerts, temperature warnings, and communication fault notification. Overall, our project demonstrates that an STM32 based embedded system can provide an efficient, reliable, and low cost EV monitoring solution with ADAS functionality. In this feature, this project can enhanced by integrating artificial intelligence, machine learning, cloud connectivity, and IoT for smarter electric vehicles.
The main.c uses to prevent the sign file from being included multiple times. Compilation error. Include common.h uses common data types and defines shared by the whole project. This file uses common definitions already available in the project instead of writing them again. EV handle type different structure stores all important informations about the electrical vehicle like acceleration pedal, brake pedal, vehicle speed, motor torque, motor temperature, SOC, regenerative brake level, power, estimated range, drive mode, vehicle state. This structure stores all the important parameters required to monitor and control the electrical vehicle. Explain constant macros. Explain that these are fixed values used throughout the program. Maximum torque, maximum speed, maximum motor temperature, battery level, SOC, vehicle efficiency, simulation scale. These fixed values define the operating limits of the electrical vehicle. Drive mode. Drive mode uses EOC, normal, and sport. EOC save battery and increase range. Normal, balanced performance. Sports High acceleration and power. Functions declaration explains only the purpose of each functions. EV initialize all EV parameters. EV read ADC, read sensor values from the hardware, set drive mode, changes the driving mode. SOC updates battery percentage, motor temperature updates motor temperature, ADC channel reads data from an ADC channel. It stores all the vehicle parameters, defines safe operating limits, and declares the functions required to control speed, battery, motor temperature, and drive modes. This makes the EV system organized, reusable, and easy to maintain. Okay. Now we will run the code in SimLab. SimLab, here we go to spare parts. We have used the potentiometer, three ultrasonic sensors, warning LEDs, buzzer, and virtual term. We uses the potentiometer as input control. Mm. Each one explains acceleration, brake pedal, SOC, and motor temperature. It controls the acceleration pedal, controls the brake pedal, adjusts battery SOC, stimulate the motor temperature. We uses three ultrasonic sensors. Front First one detect the front sensor detects obstacle ahead. Left Second one gives the left sensor detects vehicles or obstacles on the left. Third, right detects vehicles or obstacle on the right side. Warning LED or warning LEDs. These LEDs indicates different warning conditions. CLSN, co- collision warning indicator. BSDL, left blind spot warning. BSGR, right blind spot warning. Buzzers produce a audible warning. The buzzers gives a sound alert whenever an obstacle is too close to the vehicle. Virtual term. Virtual term displays system messages and sensors reading. Virtual term window shows real-time data such as sensor values, vehicle status, and warning messages for debugging. The three ultrasonic sensor continuously detect nearby obstacles. The controller process all the inputs. If an obstacle or bind spotted in is detected, the system activates the warning LEDs and buzzes. The vehicle status and sensors data are displayed on the virtual term. Now we upload the file load bin ev-bin. Now we can see the values of speed, SOC, torque, temperature, range, acceleration, brake. We can also change that one. So change values here also. Now we can see that the warning is coming. We can see that alarm is on 3. Range is 3003, acceleration 20. SOC is 99, speed is 19. We can change that one also. Now we can see that alarm is coming. Mm. See, now alarm is 0, fault is 0.1. Now we display it on the Python dashboard. Yes. Python dashboard using the command prompt. The dashboard receives real-time data from the STM32 simulation through the COM1 serial port. Right. We can see the EV dashboard. EV dashboard. Here we can see that speed is increasing, torque value, acceleration, brake, motor temperature, alarm, fault, and signal. Here speed is increasing. Now we can change values in pixel black. Increase the acceleration, decrease brake, increase SOC, decrease the motor temperature. We can see that the front obstacle is coming near the vehicle. Alarm is showing the critical fault in signal is on. Motor temperature 13.7, brake is 36, acceleration 63, range is 33.33, 3333, battery is 99.9. We can change, can decrease duration. Now we okay, now we can see alarm is 9, fault is 0, brake is 73, acceleration is 28, torque is 40.9. nanometer, speed is increasing. Mm, That's all we can access through the important values in the signal. This displays the speed variation over time, helps monitor vehicle movement. This graph records how this vehicle speed changes during operations. Bird eye shows the vehicle from the top, displays the distance of nearby obstacles, used for optical detection and collision avoidance. Alarm shows whether an warning is active or not. The dashboard provides real-time monitoring of EV and ADAS system. It displays vehicle speed, battery status, motor parameters, and obstacle detection, helping the driver monitor the vehicle safely and efficiently. That's all. Thank you.